Hi, welcome back. In this lecture, I want to talk about a set of requirements that has been formulated and designed to tell us which characteristics a quantum computer needs to have in order to be useful. This set of requirements goes under the name of the DiVincenzo criteria, from the last name of the person that first tried to formulate this set of criteria. So the DiVincenzo criteria are a set of 5 conditions initially proposed by David DiVincenzo around 2000. You can find the paper on arXiv, pointed here, and it's very interesting read, and also posted the link on Canvas. So why these criteria are important? Well, these criteria they serve as guidelines for building a scalable and fault-tolerant quantum computer that can be useful to develop a quantum application. So let's go through together these 5 requirements. The first one is related to the qubits and is formulated as follows: a scalable physical system with well-characterized qubits. So a physical system that can be represented by 2 level quantum system qubit is the first requirement. According to these requirements, there is a need for qubits to be easily controllable, so we can change a state, and the qubits need to have a very well defined state, either when measured. So state 1 or state 0. Scalable qubits enable the creation of a larger quantum system. The second requirement is about the initialization of our quantum state in the quantum computing system. So if you go to the paper, the second requirement is the ability to initialize the state of the qubits to a simple fiducial stage such as state 0. These requirements needs the ability to initialize qubits in a well-defined state. This is particularly important for starting quantum computation from a known state, from a known classical state 0, 1, 6, and when we want to input in the quantum system. And why this is important? Well, this is important because initialization errors can propagate through the quantum computation. So the initialization errors will impact necessarily the computation results. The third requirement is about long coherence times, and it is as follows. So we need long relevant decoherence times, much longer than the operation time that is taken by the so-called gate operation. That is the time taken for transforming the qubit state. So these requirements tell us that qubits should have a long coherence times, what we call T1 and T2. So coherence times determine how well quantum information can be preserved and manipulated, we saw in the previous lecture. And also longer coherence times reduce errors and enhance the reliability of quantum computation. The fourth requirement is about having a universal set of quantum gates, and this requires to implement a universal set of quantum gates that can perform any quantum operation. So we call about universal set. Universal means that we can express any operation by using this set of gates. So quantum gates are equivalent to classical logical gates, and we will see that enable quantum computation. So to have this set of abstraction, these gates that abstract the gate operation, the physical operation, is a key for building complex quantum circuits and application and algorithms. Finally, we have the fifth requirement that is about reading and measure the qubit state. So the quantum system must have a qubit-specific measurement capability. So qubits should be measurable with a high fidelity and a minimal disturbance from the environment. So accurate qubit readout is essential for obtaining computation results. This is the last slides of this lecture, and talk to you soon.